The great thing about this is you really have done the main work with this stuff. I think the hardest part of the last unit, assumptions and conditions, central limit theorem, interpreting intervals, levels, p-values, errors, powers. That was the hard stuff. You guys killed it on the math. Very few people missed any points from any of the math. That's good. Because that means the hardest thing that we're doing this unit, all of those same things, is not changing. The only thing that is changing is the math. All right, so here we have a situation. Scientists study the gripping strengths of an 11-year-old holding a PlayStation controller and a frenzied mom holding tickets to Aruba. Who would win? The frenzied mom? I always get weird responses. Like, look at that kid, he's kind of chunky. He wouldn't be able to hold on. Or the ticket's gonna break before the controller breaks. The problem with this is I cannot state these in terms of proportions. Okay? I cannot turn time into a proportion. I need to look at it as its own units. And so when that's the case, we're going to still use our sampling distribution models. And actually for the last unit, and it wasn't really last unit, it was chapter 17, we talked about the sampling distribution model. And probably the one biggest place where people lost any points on the flip book was on the sampling distributions card, because you only put the stuff for proportions. You're supposed to put proportions and means. We're going to follow the sampling distribution model for means. And the big thing here is that the standard deviation for means is sigma over root n. That's the biggest difference. We're going to be centered at whatever we see, just like with the proportions. For proportions, we were centered at mu equals p. Now it's just mu equals mu. And the standard deviation says sigma, and what does sigma represent? Anybody? What does sigma represent? That's the lowercase sigma. We've seen this before. Standard deviation of population. Remember, whenever you have those weird, like, Greeky symbols, that's going to be of the population. So sigma is the standard deviation of the entire population. This is the standard deviation of the sampling model. And according to the central limit theorem, what does the central limit theorem state? What was that? Central limit theorem said what? Bingo. The more samples you have, the closer it gets to normal. What does normal describe? Does that describe shape, center, or spread? Specifically what about shape? A very specific bell curve, which is 68, 95, 99.7. Okay, because a lot of you guys, when you hear normal, you're thinking just that curve. But it's not just about that curve. It's about the ability to use your 68, 95, 99.7, the ability to use your standard z-scores to find probabilities. Okay, so that's what we're saying. Still, the more samples that we have, the closer we're going to be to the normal model, which is centered at mu, so whatever the population average is, and the standard deviation of the sampling distribution says population standard deviation over the square root of the sample size. Okay. So just thinking about those simple little formulas. Read through this mamma jamma. I have no clue if this is in your notes or not. Nope, not in your notes. Oh, and I do want to take a second, guys, to explain your outline. It's a little bit different this time. Not crazy so. But you'll see towards the bottom, I've shaded it in a little bit. Not that it copied really well, but I shaded it in a little bit. And that's because that's chapter 25, which doesn't really fall into this unit. It's kind of its own standalone, like the College Board has it listed as its own entire unit. It's just one concept. It's just one chapter for us. It's just a very, very tiny unit. So I put it on here also. And you'll see that we will actually, just to give us a little bit of time to review, we will start it before we take the test, but that's not going to be on the test. Okay? All right. So just wanted to kind of point that out to you. You still have your flipbook rubric on the back. And yeah. Okay. So what am I asking you to do here? What are we doing? Anybody want to summarize that madness? What's the big focus? What are we doing? Come on. Fish. Like my little fishy face. Fish. What are we doing with that fish? We're finding the standard deviation of the mean weight for samples. Okay? The thing is, what is changing as we go through this? Not the mean weight. The mean weight is staying the same. The mean weight is 35 always. Standard deviation of the population is always 2. One more time. The amount of salmon. We're looking at different types of shipments. We are looking at a box of 4, a carton of 16, and a pallet of 100. As I change those samples, what is going to change? Shape, center, spread? Spread is the big thing. So how do I calculate the spread, or in this case, the standard deviation? That formula. It was up there a second ago. Can anybody tell me what that formula was? All right, we've got 3 different ends. Do it. Find the standard deviations of the mean weight of salmon in each type of shipment. I know, salmon. Salmon. Whoever came up with that, I don't know. Of what? Restaurant. Oh, God. English is stupid. That's what. Me. I believe that. German is the same way. That's why I like that language. All right, focus, guys. Find the standard deviations for a shipment of 4, 16, and 100. So in each of these cases, you should be taking 2 and simply dividing it by square root of 4, square root of 16, square root of 100. And hey, what's extra nice is those numbers. What's the square root of 4? Square root of 16? Square root of 10? Square root of 100? Dang it, 10. So the math there, super duper crazy. I want you to look at this. What is different with means that we didn't have before? When we were talking about proportions. I have something up there that I haven't seen before. Units. Okay? Proportions don't have units. Means do. Proportion is just piece of whole. This guy, you have to make sure that your center and your spread always have units. Do I expect you to write, the shipment of 100 salmon has a standard deviation of 0.2 pounds? No, I don't care. What I care to see, boom, boom, right there. Formula, answer, done. You want to write that as 1/5? Go ahead, write that as 1/5. I don't care. Personally, that requires more thinking than just type it into the calculator. Boom. All right, so this says the distribution of salmon weights turns out to be skewed to the high end. What does that mean? Is that where the big piece is or the tail is? That's where the tail is. The tail is pulling it that way. Why do you think it's skewed to the high end? Are you limited really on how big salmon can get? Well, I mean, sure, you probably at some point are. I'm not going to be expecting the Loch Ness Monster to come out in a salmon shape. Are we limited to how small a salmon can be? And when it comes to fishing and regulations and all that kind of stuff, you have to have at least a certain size because they don't want you clearing out all the babies. Okay? So that is why it is skewed to the high end. You can only go so small and still be legal. Some people go a little bit below where they're legal, but that's why the hump drops off there. But you can have some seriously huge salmon. My dad will tell you he's caught all of those. Something this big, slowly over time, caught a huge fish. Zoom in on the lens, and think about the size of his hand. He loves to fish. All right, so the distribution turns out to be skewed. That means the sample starts off not necessarily normal. Would we be better fitting the normal model for the sampling distribution on the boxes of 4 or the pallets of 100? Why? Has a larger sample size, and what does the larger sample size do? It makes the spread more normal. Central limit theorem. When we're talking about the central limit theorem, that's applying, remember we were talking in proportions about the large enough condition? We said NP and NQ had to be greater than 10. That was the central limit theorem, to be able to use the normal model. We're not going to have P's and Q's here, but we still have this thing that we have to be large enough to meet the normal model. Okay, lots of words to just say 100, more sample, more normal, central limit theorem. Okay, so what exactly changes when we go from proportions to means? I don't know. Well, the nicest thing about proportions is you only really have P. Your normal model, you're centered at P, your standard deviation is root PQ over N. P, all over the place. Ew, that sounds horrible. I just realized that, sorry. Okay, we'll not say that again. But I do. It is recorded, so yay, that was great. We don't have the ability to calculate standard deviation for means off of what the center is. They're separate. We can't do that. So when we're trying to talk about the standard deviation, we can't just use like root PQ over N. So we estimate it. Remember how we went in proportions from standard deviation when we knew something to something when we didn't? What did we call it? Guess what we're going to do now? Same thing. We're going to use the standard error. And when we talk about samples versus parameters, population parameters, the population parameters use those funky Greek letters, like sigma. Samples are just going to use S. It's like P versus P hat. Okay? When we have a sample, we're going to use S. And when you think about it, remember when we've done our 1-var stats on our calculators to find the mean, the standard deviation, the 5-number summary, Q1, Q2, Q3, that kind of stuff? You're using the button that says S because what you have is a sample. Now, there's a little bit of a problem that comes with means. That's a relatively new discovery. Means have a little bit more variation built into them. Because if you think about it, P's are automatically limited between 0 and 1. Everything is scaled to that. You can't go above it. We don't have that limitation for variations of means. That means our shape is actually going to change. What has our shape been up to now? Normal. We've been relying on the normal model. But we have a little bit of a problem with means. They vary a little bit more. So it's not one standard deviation is 68, 2 is 95, 3 is 99.7. We're going to have a little bit more variation. So that means we're going to have less in the middle and more at the ends. Okay? Beer! Seriously. Beer. This is where this came from. Well, statistics changed because of beer. Okay? William S. Gossett. Is that a name you need to know? No. He was an employee of Guinness. Okay? He was at the time studying statistics. And what happened is he noticed that they were rejecting way too many batches. Party foul. Getting rid of way too much perfectly good beer. And it's Ireland. This is Guinness. You'd probably be arrested if you threw away a perfectly good batch of beer. Okay? That's like a national treasure. They were getting rid of it. They would test the beer for certain things, certain qualities. And they were finding that they were rejecting too many good batches. What error is that? When you reject when you shouldn't have. Type 2. No, not type 2, type 1. Means the fail to reject, the first thing is type 2. You rejected, but you shouldn't have. Okay? They were making too many mistakes. So what William Gossett did is he made a few changes. And they named it the student's T model. Why the heck is it the student's T model and not Gossett's model? It's because unfortunately, when you discover things and you're not a doctoral person, if you're a graduate student or you're in your doctoral program, you do not get to have anything named after you. So he was a doctoral student at the time, and so he could not publish under his own name. So he published under the name student. I don't think he went and finished it. I don't think he was interested in that. He was heavily employed and drinking, apparently. So they called it the student's T. So now instead of talking about the normal distribution, we actually have something called the T distribution. And that's what we call it. You can call it student's T, or you can just be lazy and call it T distribution. And when we do that, by the way, it's a lowercase t. Note that guy right there. And what the T distribution focuses on is the fact that as my sample size changes, I get to be more normal. But what happens on the smaller end of things? What happens if my sample size is not really good enough yet? And they started doing something called degrees of freedom. Degrees of freedom we're going to be seeing a lot of. So we're going to do this now for means. We're going to do this for counts. We're going to do this for bivariate data. Okay, and there's a delicate balance is what degrees of freedom stands for. But basically, each degree of freedom creates a brand new normal curve with its own distribution. Do I expect you to memorize any of them? Oh, heck no. That's what our calculators are for. And for people that don't have calculators, they have tables, plural, of T distributions. And usually you're using an approximation because Nobody's got that many tables. Okay? So, here's what the student's t-distribution is all about. You have the unimodal. You have the symmetric. You have bell-shaped. Just like normal. Normal is a descriptor of shape, but in it is this definition of 68, 95, 99.7. So we're going to have center and spread and bell curve. We are not going to have the 68, 95, 99.7. But what's really cool here is a t-distribution with only a couple degrees of freedom, okay, are going to have much fatter tails. So if you look at this here, the middle part has dropped down a bit. The tails have popped up. We're going to be more likely to see the things on these ends. But as your degrees of freedom increase, this is huge, huge. As the degrees of freedom increase, the t-models are going to look more and more like the normal model. That means we're going to get closer and closer to being able to use that 68, 95, 99.7. You have to know, degrees of freedom. As the degrees of freedom increase, your model looks more normal. And if you were to do a t-distribution with an infinite number of degrees of freedom, that is the normal model. There's a certain point where they start looking so close to each other that we oftentimes just switch over to the normal model. But if we're dealing, in all of this guy, the student's t-distribution, we use t when I don't know what's true about the population. If you know what's true about the population, by God, use the normal model. Okay? How do you find degrees of freedom is going to change based on what we're talking about. Okay, everybody have their calculators? We're going to do some calculator stuff. See some people furiously writing down. The big thing that I need you guys to understand, students' t distribution looks kind of normal, but the tails are fatter. Means the hump is lower. But more degrees of freedom, more normal. All right. So use your calculator. Let's do this. Let's do this, mamma jamma. Critical values. How did I find a critical value for a 90% confidence interval when we were talking about z's? Inverse norm. Make sense? Remember that? How did we get to inverse norm? Second, vars. Z stands for a normal model. What do you think I'm going to do here? Oh! Inverse T. Okay, when I was looking for a critical value for z-scores, what did I put on the first line? 0.5. Then what? So that's going to be the only thing different here. When you were doing a critical value, you would talk about like your mean and standard deviation. Here we don't need that. Here we need degrees of freedom. I'm going to put in 17. Think. Boom. Do you see how similar this is? You just got to make sure that you're doing the right model. And like I told you guys before, if we're looking at our distributions, we have normal, inverse normal, we have inverse T, TPDF, TCDF, just like we had up here. Then we have, that guy is a chi, that's a chi squared, not chi. And yes, I will be beating you if you start saying that. There's F distribution, which we won't do. Binomial, which we've used. Poisson, which we won't. Geometric, which we've used. Was that enough for you? Enough over your head? just right over the head. All right. So we've got the first one. What's the difference? Oh, that's and the second one. Let's see if you can calculate the second one, because I was not paying attention. Awkward. Awkward turtle. If you ever had Miss Dooley, she does this. Awkward turtle. So when we were looking for a critical value for z's, we used inverse norm. Looking for a critical value for t's, we use inverse t. Do you see how we're not actually learning very much new stuff? I'm changing one tiny thing. Okay. P-value. If I wanted to find the probability that the proportion was greater than 0.75, what would I use on my calculator? How do I find p-value? Normal CDF. Guess what I'm going to do here? T CDF. So I'm going to go to my calculator again. If I can find it, there it is. I'm going to go to second vars again. Nope, I guess I didn't hit the second. And I'm going to go to T CDF. Do not use PDF with normal or T. Don't do it. Calculus, that's why. Just don't. So we're doing T CDF. And if I'm looking for this one, the p-value for t greater than or equal to 2.09, what am I going to put for my lower? 2.09. What am I going to put for my upper? And you really want to be ridiculous with means, because you can have really large numbers with means. Degrees of freedom here. 4. I am hitting 4. There we go. There you go. That was like synchronized to him dropping his pen. Sometimes that happens. Okay? So I want you to think about D. How would you do D? Dang it, I couldn't find the mute button to not cough into it. I'm just sketching here a bell. We draw, it looks basically the same when we draw it because we don't really have much scale going on here. Basically, what goes in the middle is the mean. So far, so good? Z-score, what was the interpretation of a Z-score? Who remembers the interpretation of a Z-score? The number of standard deviations away from the mean. So what do you think a T-score is? Same exact thing. Number of standard error or standard deviations away from the mean. So this says on part D, p-value for an absolute value of t. So what numbers have an absolute value of 1.78? 1.78 and a negative 1.78. And if I'm looking for that absolute value to be greater, where am I looking at? Outside. Anybody understand that? This is what I'm looking for. Using that mental picture, how could you calculate the p-value? Probability that you're under those regions. It's like a two-sided test. Remember, we have a couple of options for a two-sided test. Yeah. So what we would do here, exactly. I usually start with the 1 minus, so that's already in the calculator, but I don't care when you do it. Then I'm going to do CDF. What's the lower? Negative 1.78. What's the upper? 1.78. And my degrees of freedom? Oh, okay. So that's right under the 8. And there you go. You can do it that way. You could also do TCDF from 1.78 to crazy 9s. And then do what with that? Times it by 2, because I just calculated this right-hand side. So you can do that times 2 and get the same answer. I don't care which one you do it. Okay? And again, we did that by thinking about the idea that when we're saying the absolute value is greater, that means that we're further away. Another way of thinking about that is saying the not equal to the two-sided test. Okay. Hard question. Not. Yes. No, thank you for asking that. What he just said is, does it matter if, like for C, it says equal to, this one doesn't have it? Doesn't matter at all. And it actually goes calculus. What's the area under 1.0? So we don't need to really worry about the difference with that. Okay. So that don't ever let that throw you off in here. All right. I want you to write this down. These 2 problems are very common multiple choice and free response. Especially now with the AP exams. Our AP exam is moving further and further away from straight up calculations because they're like, dude, calculators do that. And more towards interpretations, understanding the whys. Yes, ma'am. Why? It is true. When you cut back on your type 1 errors, because that for a manufacturer, that's their biggest worry, because you're throwing away money that you could be making. When he started accounting for that difference, Guinness started making more and more money because the ends came up. And what he realized is instead of, like, for example, 2 standard deviations being 95, with what they were doing, 2 standard deviations was closer to 90. Having rather than 5% on the end, you'd have like 10% on the end, depending upon your degrees of freedom. And so in making the observations that he saw and doing the tweaks that he did to it, it's really kind of cool. It's really a T distribution is a combination of Z distributions. They're kind of all layered on top of each other. It made the company more money. And it started off with beer, and then they realized they could apply it towards absolutely everything. And so the T distribution is now used all of the time. Normal distribution we can only really use for proportions, or if I absolutely know what's true about the population, which rarely is the case. So this cuts back on those type 2 errors. All right, so tell me, how does the shape, center, and spread of T models change as the number of degrees of freedom increase? Shape. What happens to the shape? More normal. Understanding that normal talks about that 68, 95, 99.7 rule. Any distribution can have a standard deviation. Just because you have a standard deviation doesn't mean that you're normal. Okay? Center. Stays the same. Spread. This one we haven't quite talked about. It's not going to be more spread. The thing is that for us, the degrees of freedom are tied to your sample size. So you actually have less. Because if your sample size increases, your degrees of freedom increase. So your spread is actually going to get closer to normal, and typically what will happen is your spread will decrease. It says spread of the t-model decreases as the number of degrees of freedom increase. Okay? And again, that's because, at least for now, for our means, our degrees of freedom is tied directly to our sample size. All right, so for number 6, it says describe how the critical value of t for 95% confidence interval changes as the number of degrees of freedom increase. So maybe what you can do here is, how do we find the critical value for t distribution? What did we just do? Find the critical value, you use what on your calculator? Inverse t. So start. Pull up your calculator. And I freaking love these calculators because I'm going to the inverse t. We're talking about a 95, so I'm going to do 0.5, bless you, plus 0.95 over 2. And you can start with the small degrees of freedom. So like the smallest you can go, they're always going to be integers, at least for now. That's the inverse t for this. What I can do is I can do second enter and just change that last number. Look at how big of a change that is, from 1 degree of freedom to 2 degrees of freedom, to 3 degrees of freedom. Well, that's 23 degrees of freedom. And keep going and tell me what's happening as we get a larger and larger degree of freedom. What's happening? It's getting smaller. Is it getting closer and closer to 0? Like if you're talking about calculus, does this have a limit of 0? Let's tack one more 0 on there. Is this getting closer to a number you might have seen before? What number have we seen before that this seems to be approaching? The z star. So let's do inverse z, so inverse normal, for the same idea. 0.5 plus 0.95 over 2. And that's what it's doing. Okay? Statistics and calculus are very closely tied. You're welcome that we are not doing it using the calculus formulas, because that's painful. That's a painful, It's all college. College is fun. I liked it. But do you see what I'm talking about here? That when we start with relatively low degrees of freedom, look at how far off we were from the normal model. We started off, for crying out loud, at almost 13. 1 degree of freedom was almost 13. 2 degrees of freedom knocked it back to 4.3. 23 took me to 2. By the time I was up to basically 1 million, I was at 1.96. And when I switch over to the inverse norm, look at how close those are. They're very, very close. So yes, there is a certain point in time where we can switch from the T model back to the Z model, because the Z model has some numbers that we're more familiar with. So as, and this is what we're looking for, as the number of degrees of freedom increase, T star starts to approach Z star. Okay, so I've just summarized all that up. As your degrees of freedom increase, T star approaches Z star for the corresponding confidence level. Okay, small degrees of freedom, it'll be way off. Bigger the sample size is, the more degrees of freedom that you have, the closer it ends up being to that normal model. Chris is just so enthused right now. You need to contain your excitement here. Rein it in. What the? Did I call you Carissa again? I keep doing the two of you. I don't know why. I have no words.
That was like, I didn't get like, that probably did.
Are you serious? Are you serious?
So like, she thinks I'm somebody else. Like,
I
there I wasn't thinking
Okay, I admit, I absolutely suck at names. I had a best friend in college, roommate in college. I still called her, it was Woodley and it was Maggie. And I still call them by the wrong names. Because, I graduated from college all of 5 years ago, right? Just kidding. But yeah, no, it's nothing personal. I just suck. Shut up, leave me alone. Stop making fun of me. I never claimed to be perfect. All right, so similarities and differences. How much do I need to reevaluate? How much do I need to change from what we did with proportions? Not much. Main ideas still hold. A confidence interval is still based off of your sample, and it's still centered at what you saw. It still goes, out in either direction. It's still symmetric in either direction. That's not changing. Confidence intervals are how confident are you, not necessarily in your particular sample, but in how you got your sample. Okay? Hypothesis tests. Still focus on the hypothesis, the parameter that we think is true. This has not changed even the tiniest bit, which means when we come over here and look at all of our interpretations, the only thing that's changing is instead of the true population parameter, instead of that being the true proportion, it's now going to be the true average. Same here. Instead of containing the true population parameter, instead of the true population proportion, it's now going to be the true population average. The parameter is no longer proportion, it's an average. Mind blown, right? Massive change. P-value stays the same. Errors, exactly the same. Power, exactly the same. We're just using means instead of proportions. What? Okay. So, that means what you hated about proportions, you're going to still hate about means, which typically are going to be your interpretations. So what we're looking at here, I don't know if any of them are correct, if all of them are correct, if all of them are incorrect. We are interpreting the interval. So I want you to read through these, guys. You can discuss it with each other. Is each of those A, B, C, D, E correct or incorrect? You'll probably want to talk with each other. Come on, guys. Let's focus up here, please. All right, so for this, there is the easy way and there is the hard way. Easy way? You sure you want the easy way? Positive? No. The hard way is looking at each and every one of these individually and try to figure out if it's telling the truth. The easy way is to look at the question, what am I interpreting? I'm interpreting the interval. So if I come over here and I look and I say, interpreting the interval. Based on our sample, we are 95% confident that the true mean weight gain the supplement produces is between 45 and 67 pounds. The smart decision is to ignore all of these, and that's true for your multiple choice questions also. Ignore that. Go straight to this. Think, interpret the interval. Interpreting the interval says, based on our sample, we are 95% confident that the true population average mean weight gain for the supplement is between 45 and 67 pounds. And then you just say, is that what that said? No. This says 95% of the cows studied. Do I need an interval that talks about the ones that I actually saw? You don't ever need an interval for your sample. You have your sample. Why do you need an interval? Do you understand what I'm talking about? The next one. What's wrong with this one? It's saying for certain, and our confidence interval is about the whole entire population mean. This is talking about one specific cow. Do you see the problem there? That's not an average, that's one cow. Okay? What's wrong with C? Do I need to guess what the average weight gain was for cows in this study? No. I know what the cows in this study weighed. I don't need to guess. Okay, yep, squeaky voice. The average weight gain of cows fed this supplement will be between 45 and 67 pounds 95% of the time. So we have average weight gain of cows fed this supplement between 45 and 67. Is a confidence interval about 95% of the time? No, it's not a statement of probability. It's saying, based on my sample, this is how many samples we think should actually capture the truth. And it has nothing to do with any other sample. Confidence intervals is trying to go from our sample to capture what's true about the population on average. None of those were true. Don't assume. Okay, does it make sense going through that? Do you understand what I was saying, where if you just start with the sentence you want, it's easier to figure out which one doesn't match? Because otherwise it's like, oh, look, words. Total glaze over. No idea what this is saying. All right, let's try another one. I'm just letting you know that we created a T interval here. We have our 90% confidence. This is just saying that the average teacher pay between those two numbers. Okay, we're going to be getting more and more into actual computer outputs, what those are going to look like. There's little pieces wrong with many of these. Some of them are bigger pieces wrong. So I'm going to look at the first four Because all of the first 4 have something in common. What's that thing in common in the first 4? 9 out of 10. If we took many samples, 9 out of 10. Which is that? Is that an interval or a level? That's one more time. That's the level. Because the 9 out of 10 represents the 90%. You understand what I'm talking about here? 9 out of 10, that's the level. So we want to see, does A, B, C, and D, do those guys match the interpretation of a level? What does the interpretation of a level say in this context? If repeated samples were taken, we don't know what the size is. These guys all say 9 out of 10 of them would. So we're talking about the different samples, so this is the level. This isn't about our one specific interval. It's about when they say about 9 out of 10 of them would produce, about 9 out of 10. So, right, it doesn't tell you, because some of these are strictly interpreting levels. Some of these are strictly interpreting intervals. Some of them is some weird cross product of those. Oh, yeah, sorry. I didn't even see that. 288. Yes. So the interpretation of a level here is, I would say, if repeated samples of 288 were taken, about 9 of the 10, resulting 90% confidence intervals, would contain the actual average teacher pay. Do you understand what I did there? Versus the interval would say, based on our sample, we're 90% confident that the true average teacher pay is between $38,944 and $42,893. Is A true or false? False. Why is this false? It's saying produce this confidence interval. Samples will all give me different confidence intervals. I'm not going to tell you that that exact answer is going to happen again. What about B? True or false? I'm hearing both. Confidence level. If repeated samples, if we took many random samples, of size n were taken, about 90% of the resulting 90% confidence intervals would contain the true population parameter in context. B is actually true. For those of you who are saying false, why are you saying false? Because what? And that's not a deal breaker. Specifying the sample size, not a deal breaker here. What about C? Is C true or false? False. Because we're not talking about specific teachers. We're talking about what? What does that mu stand for? Average. We're not talking about specific teachers. We're talking about averages. What's wrong with D? Do I need to make an interval about my teachers surveyed? No. May or may not be true. And what is wrong with E? Say it again. It's in the United States. I will tell you right now, if that was the average pay for teachers in Prince William County, there would be no teachers in Prince William County. You could not survive on that. You would be living in subsidized government housing at that pay. That is the Nevada sample average. Do you understand what I'm talking about? You can only, and this is huge, what we're focusing on here are the areas where you guys have trouble. And you have trouble because you're zoning out, drifting away, falling asleep because you don't think this is interesting. I don't care. It's amazing. You've got to be awake and paying attention to it. What we're trying to say is whenever I take a sample, I can only infer towards a larger population that sample is representative of. Teachers in Nevada are not representative of teachers in Georgia, teachers in New York City, of teachers in Los Angeles, in Alaska. They're not the same. You can only infer out to teachers in Nevada. So that's why the only one that was correct was B, because B talks about if we took many random samples, 9 of the 10 of them would produce a confidence interval that contains the true average population parameter. Okay. So I want you guys to write this stuff down. Take your answers, see what you can do with this. Beautiful. That's it. Based on our sample, we're 95% confident that the true average pulse rate of adults is between 70.89 and 74.5 BPM, or beats per minute. Okay with that? And guys, these outputs will always give you redonkulously long decimals. It really is only limited to the size of the screen. Because I've played with these outputs before and I've seen what's happened. And they do that because all you're putting in is data. It's going to do the calculations. It's not saying, well, in context here, I think it would be better to round it out to the nearest whatever number of decimal places that is. No, you have to do the thinking. How do I calculate the margin of error for this interval? No. Gleb. Find the differences and divide by 2. So about what do you get? About 1.8. If you want to take it out farther, you're just a dork. Stop it. Because you take 74.5 minus 70.89 and divide it by 2. Okay? If we had calculated a 99% confident interval, would my margin of error be larger or smaller? What would it be? It's a A or B question. It would be larger. Why is it going to be larger? Bless you. Right. To be more confident, you have to account for more variability. Beautifully put. So if I want to be more confident, I am going to be 90% confident that the high temperature tomorrow for Battlefield High School is going to be 52 degrees. Plus or minus 2 degrees. If I want to be more confident, what am I going to do? Be more sure of myself. Plus or minus 20 degrees. Yes. I probably wouldn't value anything you said if you said plus or minus 20 degrees, but hey, it is Virginia, you never know. Okay? I'm kind of getting into the, I don't know what this is that I'm doing right now, but it's fun. What is that? Tai Chi? Or airbender? Okay. All right, let's see here. All right. Here comes more of that what is different game. One of these things is not like the other. One of these things just doesn't belong. Yeah, I'll try not to sing too much. Assumptions and conditions. Hey, guess what we still have? Independence. All right. Think back. All of a couple of lessons. What met the independence assumption? What did we have for proportions? Random. Random. It's not just a state of mind, it's a thing for statistics. So for your independence assumption, to meet that idea that they are independent, the first thing that we have is random. Does anybody know why random is important? What does random do? But why? You dork. It means they're independent. Where's X? There it is. We need them to be random because if you think not random, means you're picking things with a purpose. That means that I'm going to pick things that have certain characteristics that tie them together. That means not independent. Okay? So random gets me the idea of trying to be a representative sample without any bias. Okay? And independence is needed because you want everything to have the same opportunity, the same probability. Okay? So the random condition we usually get from either a randomized experiment, random sample. Typically they'll say randomly sampled data in SRS. Those are good. You can use, as long as you have random in that, that's okay. What else did we have for independence? Randomization, 10%. What did the 10% condition talk about? Not too big. And we have that 10%, that not too big, because once you start drawing without replacement, pulling them out, the probability of selecting the next guy is going to start changing by enough where it can affect the outcome. Okay? So, hey, this hasn't changed at all. Okay, so we had independence, which was mainly my random and my 10%. What was my other one? Sample size. And for proportions, that was success failure. We don't have successes and failures with averages. So we're not going to have successes and failures with this. Our sample size assumption, still the same idea. We want it to be big enough. We want it to be big enough so that we can assume normal. So that 10 success failure, that was saying, okay, we're big enough to use the central limit theorem with proportions. What do I need to meet the normal assumption for means? It depends. It says that we really can't ever be certain that a population that things come from are normal. Heck, there are a lot of things that are as abnormal as humanly possible. There's bimodal. If you're talking about heights of, let's say, 8th graders. You're going to have the girls, you're going to have the boys. Because 8th grade is a fun year. You know what I'm talking about? Guys are all kind of like middle, and the girls are all high. Okay? Or you could be talking about income. Most people are down here. Billionaires, over there, heavily skewed. Not every population starts off normal. But we get, by the central limit theorem, that a sampling distribution approaches normal because of what's called the nearly normal condition. The nearly normal condition says, if your data comes from a distribution that is unimodal and symmetric, go ahead. It's nearly normal. You're pretty safe. It's kind of like saying you pass your success failure condition. Nearly normal, we're good. How do we do this? We will be doing this by either using a histogram or what's called a normal probability plot. An NPP is what we refer to it as. I generally do the NPP because it's a bunch of dots. And to me, dots are easier to draw than boxes. And the good news about histograms with this case, we don't need to be careful about bin widths and all that jazz. We're just looking for shape. We're not trying to be perfect. So it's just histogram draw. But we will be looking at a histogram or normal probability plot. The smaller your sample size, the more closely it should be normal. Smaller the sample, the more normal it should be. So a really small sample, you want to see a nice unimodal symmetric bell curve shape. Normal probability plot, you're looking for dots that line up in a nice diagonal line. Then you'll see that when we get to it. When the sample size gets bigger, we can say, all right, well, as long as it's generally unimodal and you don't have crazy outliers, we're good. The normal probability plot, that means we're looking for something that's generally in a line, but you might have a little wiggle to it. For a big sample size, we're usually safe. And so this is really the piece here. If you have a sample size and there is no set in stone number that says large enough, but generally we kind of look at 30. If you have a sample size of 30, we can normally say, by the central limit theorem, assume normal model. Okay? We can do that because it's a larger sample size. And if we were looking back at the Z stars, once I got up to like 30 in my degrees of freedom, it's really, really close to the normal model. So that's why we can do that. Okay? This is going to be a visual thing, though. If I do not tell you that either the population it comes from is normal, or you have more than 30 in your sample, you need to have a picture. And with this class, I'm not normally going to be giving you 30 data points to work with. That sucks. Trying to type all that stuff in. You'll normally have something like maybe 10, 15, 20 data points. So you will have to draw a histogram or normal probability plot. Okay. All right. So just a few things. Whatever we don't get through here today, that's okay. When you have conditions met, we get to use our confidence interval. And hey, although that might look a little bit weird, this is the exact same thing. Observed. What do we call that? How do you say that? Y bar. That's just the average of your sample. Observed. Plus or minus. Test statistic. Times standard error. And you see this little n minus 1 here? That n minus 1 is the number of degrees of freedom that you have. So if ever you're trying to find the degrees of freedom for just what we're doing right now, depending upon your test, that formula might change. But for right now, the degrees of freedom is n minus 1. And then we've already said the standard error was s over root n. So this has not really changed. Observed, plus or minus, test statistic, standard error. Our observed is now an average. Our test statistic is now t, with degrees of freedom. And our standard error now is just s over root n. And this is just saying for right now, degrees of freedom is n minus 1. Okay? So, what's this next one? Okay, so we'll stop here. And let's see where we are. So we will do more of that practice next class. Your homework is already posted, the My Math Lab. Okay? Please do not miss class next time because we're going to be doing a lot of work with calculators. We're not doing many of the calculations, but you need to know how to work your calculator. Okay? All right, we'll stop there then.